So it's a pleasure to introduce the second speaker for this session. Shun-Qing Zhang will enlighten us about non-planar integrated correlators in N equal 4 super Young lists.
Oh, yeah, can you hear me? Yeah. Okay, cool.
Please take it away.
Thank you. So just try. Okay. Yeah, thank you very much, and it's really a great pleasure to be in this conference. So today I will talk about this non-planar integrated correlators in N equals 4 super Young mills. So we have heard a lot of interesting talk regarding these topics on Monday. And today I will focus on this subject from a more perturbative point of view. So it's based on the work with Kong Kao at Queen Mary and this recent paper on this non-planar correction. Okay. So it's a quick recap on Daniel's talk on Monday. So basically we're interested in these 4-point functions of 4 stress tensor operators. And because of the superconformal symmetry, you can factor out these prefactors, and you only focus on this the dynamic part of it. And it's a 4-point function, so it's a function of cross ratio U and V. And by integrated correlators, we mean we further integrate this quantity over the space-time coordinates, and you can relate this to the supersymmetric localizations and obtain the exact result of it. And just more information about this dynamic part. So in the weak coupling, it has been widely studied. So the perturbative integrand can actually be written down up to 10 loops in the planar limits. And for the non-planar sector, it's more complicated, but still can be determined up to 4 loops. So using the result from the localization, so since you have the exact result, you can just perform the small g Young mills expansion. Then you can see this very simple, remarkably simple structures in each loop order. So the small a is just the two-loop coupling. So you see the 1 loop, 2 loop, and 3 loop expansion. Then you can observe that each loop order, you only have the single zeta value. So zeta 3, zeta 5, zeta 7 appears. And the first non-planar correction actually shows up at the 4 loops. So here you can see the 1 over n squared. So it's a genus 1 graph. And so for this talk, I'll just try to use the unintegrated correlators. So you can express them in terms of some Feynman graphs. Then you perform this integration, and you can actually see when you're adding up the Feynman diagrams, you see that each diagram has many different kind of zeta values. But when you sum them out in the consistency way, you see that they get canceled out and give you this very nice structures. So it's just not a single zeta canceled out. Also, this like a rational number prefactor also agree with the localization result. Okay. So it's just some notation I want to, some terminology I want to fix. So this is the dynamic part I referred to. So at the weak coupling, you can further do this loop expansion. So in the literature, people call this capital F L loop. So 1 loop is just a box integral, and the 2 loop you have a ladder, 2-loop ladder, and the product of 2 1-loop box. And the 3 loop you start have the ladder integral, but you start have the tennis court and easy and hard integral. So this is like just in the literatures. So this is the unintegrated correlator in the loop expansion. And by integrand, I mean this smaller f. So it's a rational function from external 1 to 4 points. And you have the loop insertion point from x phi. So 1 loop is x phi to 4 plus L. So this smaller f has a very nice hidden symmetry. It's because the O2 operator is basically in the same multiplet, the stress tensor multiplet as the Lagrangian insertion. So that's the loop integral. So this smaller f, the integrand, respect the 4 plus L symmetry, permutation symmetry. Then when you integrate the way the loop expansion is done, give you a different structure of the 4-point conformal integral. But so this I call the unintegrated correlators before integrated spacetime. It's best known up to 3 loops. So it's a very complicated Poisson logarithm by this group computed. But if you want to directly use the result and you further integrate the spacetime, it's very, very difficult because it's like 10 pages of the Poisson logarithm. So you have to do some tricks. And furthermore, because I'm interested in the for loops, so even this capital F at the for loop is not known, so it's impossible to basically use that result. But later on, you can actually use this smaller f, the integrand. Then you perform this is called a period. Basically, you integrate all the space, all this x. Then what you left is just a zeta value. So this basically bypass this capital F, then directly give you the integrated correlator for each individual Feynman diagram. So let's see some examples. So just as I claimed, the integrated correlators in the perturbation are those periods of the F graph. So F graph is just a graphical representation for this smaller F integrand I just showed you. So it's known up to 10 loops. So here are the F graph for 1 loop, 2 loops, and 3 loops. And the way you read this F graph is you look at the vertices, and each one has a conformal weight 4, which means it has 4 edges attached to it. And if you look at these blue vertices, it's because it has 5 propagators, but also it has a numerator to connect it. So all the graph here has a conformal weight. Each vertex has a conformal weight 4. And you can count the number of the vertices. So here you have 5 vertices. So it's 1, 2, 3 for the external point, and 1 x5. So this is 1 loop. And 2 loop, you have 6 vertices. So you have 4 plus L vertices for the L loop graph. Now you start to perform the period integration. Then you find it's because it's basically like a vacuum graph. So what you get is really a zeta value numbers. So you got zeta, so you just parameterize it, and you got zeta 3, zeta 5, and zeta 7. Right. And here you can read in the denominator there are some graph vectors. So it's basically I permute this permutation explicitly. And for some graph, for example, if you exchange these 2 blue points, it's the same graph. So you have to model out some graph vectors. But of course, all these factors here has to be very carefully taken care of, such that you can produce the result to match with the localization. So immediately you can see the first 3 orders. Those are very familiar number I just written down in the first page. Those zeta 3, zeta 5, and zeta 7 is what does all this rational number prefactor just perfectly match. Okay. And I'm sorry. And now it's just because the last page I'm basically doing all the integral in the X position space. It's just for people who are more familiar with the position space. So you can also translate some of the planar integral to the usual momentum space Feynman integral. So the operation is when you do the period, you have to freely choose 3 points to be infinity, and 0 and 1 to be the external point. So this one was the first this diagram, the 1 loop diagram, the simplest one. So I took the top point to be the infinity. So all the edges attached to this point will drop off. So what you left is this the base, the rectangular in the base. Then you choose 0 and 1 to be external. So you further remove these edges. So what you get is basically this diagram. Then you just use the usual planar duality to rewrite it into the momentum space. So in this one, if you really do the integral, you just get 6 zeta 3 over p squared, and you normalize p squared to be 1. So just to convince you, this 6 zeta 3 is really the result. But of course, if you want to do this for a higher loop, it would be very complicated. So if you just do this integration up to, say, zeta 7, you would be, if you use the hyper-int, you would take like half days or something. But for this kind of period, there's a very nice program it's called the hyperlog procedure by Oliver Chenetz. So basically, you just give the integrand, and you compute the period for you up to 4 loops. So here there are the 4 loops. So it has 3 different topologies. And use the hyperlog procedure, it gives you this 252 and 168 zeta 3. Then you have to consider this, again, the graph symmetry factors. So you're adding all these factors all together correctly. You again reproduce the planar result from the localization. So now we're more interested in actually the non-planar correction at 4 loops. So it's actually more involved. Now, in the planar, you have only 3 topology to sum up. In the non-planar, you got 32 topology, including the first 3 planar topology. So it's very nice, in this very nice paper that determined all these coefficients in the 32 polynomial. then you basically use the hyperlog procedure. You compute all the period of this graph. But up to for loop order, even the hyperlog procedure becomes very difficult to compute all the diagrams. But you can use the trick that you can see there are many zeros in these coefficients. So you can use some grand determinant condition to basically kill the graph, which you cannot compute. And then at the end, this is the best representation for this the coefficients. Then you notice that their multiple zeta value shows up, but they cancel when you sum it out in this correct way. And again, the other product of zeta value have to further cancel among this diagram. Then what you left is really a single zeta 9 with the correct rational prefactors. Okay. So now, so basically, that was the first correlator. Thank you. So as Daniel pointed out, it's very complicated to do the second correlator. But actually, if you look at the perturbation, it's relatively simple. It's just like one extra box integral attached to the original correlator. So you can look at the one-loop diagram. So this one, again, is the original one-loop graph. So what I do is literally just attach a box to it. Then now you can see there's a pyramid on the top, another pyramid on the bottom. Then it forms an octahedron. And we have seen this diagram before. It's exactly this diagram, right? It's also an octahedron, then evaluate to zeta 5. So now here, what I have is, again, like a zeta 5, and I have to sum over some numerator. So I got 320 zeta 5 here. So I sum it out, I got the 60 zeta 5. And you again agree with the localization result. But the two-loop second correlator is more involved because it depends on different way you assign you attach the box to. So for example, here the black points are connected, and here the black points are apart from each other. So it gives you different values of the zeta. So again, you have to sum over these two different topology. Then you got this agreement as a zeta 7 and product of zeta 3. But for this higher loop, you can imagine you have many more different topology. You have to attach this box to the tennis court, to the lattice. But again, when you sum in all this zeta value, you got a very nice zeta 9. And in particular, you see each diagram has a zeta 3 cube, but they have to cancel it out in the second correlator. So basically, the conclusion is I hope I convinced you all this first and second integrate correlators are just the periods of the F graphs. And of course, you can, the next order would be the zeta 11 integral. For the second correlator, it also has the non-planar correction. And also there are so many different types of integrate correlators in this conference, or this n equals 2 and Wilson line and determinant operator. I think it would be very interesting to understand all these integrate correlators, even in the perturbation. Thank you very much.
Yeah, thank you very much for a beautiful talk and giving a lot of time for discussion. Let's open the floor. Who wants to have the first question?
I have a microphone here. Can I use it directly?
Why do you have a microphone?
I don't know. It appeared at certain point.
Magic.
I was just thinking, I mean, till now you basically, is it working? Okay, sorry. You basically use all the perturbative the previous perturbative results to show that somehow it agrees with the expected localization result. Mm-hmm. Can you, in principle, then do the other way around? So use localization as a constraint for going on in this perturbative expansion?
Yes, it's an excellent question. So actually, what I did previously, planar up to 4 loops. Here are 3 topology. If you further go to the next order, 5 loops, there are 7 such topologies. And use the hyperlog procedure, you can only compute 6 of them. So the left over one, actually, you can say is predicted by the localization. But later on, in Konkow's paper, they can use some relations among the conformal integral at that order, and finally confirm that prediction from the localization was correct.
Thank you for the nice talk. Have you tried playing with different gauge groups? The reason why I ask is... So Paolo and I played with the first integrated correlator, and we actually showed that there is a single expression, at least in perturbation theory, for any gauge group.
Sure.
It just depends on three variables which are called Vogel parameters. You want E6, you put some numbers. You want SUN, you put some other numbers. But the formula is just one. And in particular, the non-planar corrections, they change dramatically, because if you're doing, say, F4, there is no planar or non-planar. That just gives you a number.
I see. So actually, the expansion I first written down should really work for the generic gauge group. What you change is actually the central charges and the two-hook coupling.
Yeah, so for central charges, that's the dimension of the Lie algebra. A is the second Casimir times G squared, but the non-planar one, they get more complicated.
Yeah, so indeed, in the literature, there's no available data for other gauge groups. So SUN is really the available one I can use.
But you have the diagrams, right?
You have this.
You're computing the Feynman diagrams. So
right.
Is it possible to just adjust those Feynman diagrams?
So I think the problem is the main task is actually those coefficients are for SUN.
I see. Thank you.
Do you know which periods Hyperlog procedures can compute, and if this could be extended?
Which theories?
Which periods?
Periods.
And which one not?
You mean those?
You just said there are some periods that Hyperlog procedures cannot compute.
Yeah, so usually for those with the numerator will be more challenging. But it's really no a fixed statement or boundary cutoff to tell it will work or not. But if it works, it's very fast, within seconds. But usually if you have up to, say, 3 numerators, it will probably fail. It's the rough counting.
But you don't know why exactly?
Yeah, I think Oliver Chanez is trying to definitely improve this program, but so far, with numerators, it's more challenging.
Thank you.
Further questions?
So thanks for the nice talk. So in the last slide, you mentioned the possibility to extend this kind of approach to unequal-to theories. Mm-hmm. Could you elaborate a bit more on this?
Right. I think the first thing is to understand the measure, right? You're integrating the UMV. So for n equals to 2, to be fair, I'm not very sure if the measure is already translated to the weak coupling. For I think the determinant operator, probably Francesco would know. There's some progress, so some lower loop is already known. So they can really compute up to 2 loops or something. But for n equals 2, I'm not very sure about. Yeah.
Okay, but if you know the measure, then you also know the diagrams that you have to consider to do the computation. It's something that...
you mean the Feynman diagrams?
Yes, right.
So for giant correlator, I think it's still the F graph. Just the way it's not S4 plus L, because now you have 2 operators. So you have S2 plus L cross S2. But because for the measure for n equals to 2, I'm really not sure, but probably that case can kind of illustrate a bit this strategy.
Okay, thanks.
For n equal to 2, the story of Heslop and friends is not known, right? That requires really n equal to 4 to have this symmetry and construct the graphs.
Yes.
So not only you need the measure, but you also need to sit there and compute the Feynman diagrams or having something similar.
Yeah, indeed.
And do you have a general understanding of the mixing of different transcendental weights, like over there, 10 and 11 coexisting?
So you mean here?
Yeah.
You mean the second correlators?
How this varies if you go up and down in loop order or non-planarity. How much bandwidth is there? How many different transcendental weights mix at a given order?
Okay, so I think here is really So what I can tell you is I have a single zeta, and you can at most has a product of zeta. That's it. You cannot have any more complicated structure for the second correlator.
Oh yeah, you're right. I agree. This is also an interesting structure by itself. And I was mostly curious whether you have a general understanding about weight 10 and 11 mixing here at a given order in coupling and non-planarity.
Right. To be honest, probably short answer is not. Have to really look at it.
You can compute them. You can compute them. And so for the double zetas, they have uniform transcendentality. And in fact, you see that there's 5 squared, 3, 7, and 5 squared again. And as you go in higher and higher loop orders, just the spreads get bigger. So let's call the loop order W. You go from all the product of double zeta up to weight W. You find all of them odd. And then I think for this, the single zeta one, you just get W plus 1. You just get a single one. Yeah.
Yeah, that's perfectly the answer that I was hoping to get. Thank you.
No uniform transcendentality in particular.
Yeah.
But okay, maybe a shifted version where to each F generator for the zetas you subtract a unit of weight. Mm-hmm. Oh yeah, that's beautiful. Yeah, then I suggest we thank the speaker again for a very nice talk.
Thank you.